Hey guys, welcome back. So today we're going to do a tutorial on caustics, which are these patterns you see here, commonly seen at, say, the bottom of a pool, but generally created whenever light is passed through a refractive medium. So there's actually not a ton going on here. It'll be pretty easy to create this setup, and so you can see, it gives us quite a bit of flexibility to play around with different parts of the visual experience to really have a range of effects from what is ultimately going to be a pretty simple little network. So let's jump in. So like I said, this is all we're looking at. So it is a pretty simple network. Most of the work here is being done in a GLSL top, but don't worry, we're talking a handful of lines of code, nothing too crazy. So we will, as always, recreate all of that from scratch. But before we do that, let's jump in and do a bit of theory. So I'm going to try something new today and see if I can get my drawing pad to work. So bear with me. It might be some technical difficulties, but hopefully it makes things a little bit clearer. So let's talk about what's going on. We are going to have a refractive medium, in this case, a water with a surface that has some sort of elevation change that's going to cause refraction to occur differently depending on where rays hit it. We are also going to have a flat intersection plane that our caustics are going to be projected onto. So we will have rays of light, and in our simulation, we're going to make one or two simplifying assumptions. One of those is going to be that these rays of light are coming down directly vertically. And in our case, that's going to be from the y direction. So these light directions, let's say light direction is going to equal 0, -1, and oops, there you go. Like I said, a little bit new. 0, and that's going to be our light direction. So once these rays of light are passing through our medium, they're going to be refracted, and all that means is they're going to change direction. So as the light scatters, we'll see that there are more rays of light that end up pointing at specific locations than others. And all caustics are is a collection of concentrations of these different refracted rays of light. So where there are more refracted rays aggregating, like for example here in our diagram, there's going to be a brighter line, and that's going to be what determines and creates our caustic texture. So to do this, all we really need to do is take a light ray, figure out what its new direction is going to be by refracting it, and then intersecting that refracted ray with our intersection plane. We'll render this by keeping a collection of points where those refracted rays intersect with our intersection plane, and then we'll just render those points via an instancing network, which I think will be pretty familiar to everybody. So to do that, we're just going to need a couple more bits of theory. So first things first, we're going to need to be able to define both a ray and a plane. So a plane is nothing more than a two-dimensional collection of points. A plane is generally defined by two things. One is a normal vector, and another is simply a point on the plane, which we'll call P naught. So what this gives us is both a point on the plane, which is generally used to mean or to signify depth from origin. So P naught is going to be a point on plane, and that's really going to give us the height. And then we have our n, which is going to be the orientation normal. Orientation normal. And now one key equation that's going to be helpful here is the fact that when you take the dot product of any vector with a vector that is orthogonal to it, which obviously is the case with all normal vectors, you get a result of 0. So let's say we have some other point on our plane here, and we'll call that P1. So we know that the vector P1 minus P0 is going to be a vector on the plane, right? And so we have this vector on the plane, and we know that that is going to be orthogonal to our normal vector. So we know that P1 minus P0 dot n is going to equal 0. Cool. So let's call this equation 1. Next, we need to figure out how to think about array. So array is going to have an origin, which we'll call RO. We'll call RO. It's also going to have a direction, which we'll call RD. And then finally, there's going to be a length. And that length is going to be, in our case, T. All right, so then we have a parametric representation of our array. So we can then define any point P on the ray with the equation P equals the ray origin plus the ray direction times the length of the ray. So then how do we put all of this together? Let's say that we have our ray and a plane that it is passing through. The plane has a normal, and let's say that it intersects the plane here, here, at P. And then we're also going to have a P naught on our plane. And cool, P naught on our plane. So given that we know a plane, we know what the normal is, we know what the point is, we're going to know the ray direction from, again, the light that we refract. We're going to know the ray origin, which means the only thing that we don't know and are going to need to calculate is T, which in this case is going to be the distance from the ray origin to the point of intersection with our plane. Once we know T, we'll be able to plug it in to this equation and then calculate exactly what our 3D space location is for the point of intersection, which will then be what we're instancing. So how do we do that? Well, we do that by simply taking equation number 1 and substituting equation number 2 into it. So let's call this P1. And so now if we replace P1 in equation number 1 with equation number 2, we get something like this. Ray origin plus ray direction times T minus P naught dot N equals 0. And this is great because now we have one single equation with a single variable that we don't know. And this makes solving for things pretty easy. So doing a little bit of algebra, and by with that I mean basically just distributing this dot product and then rearranging terms to isolate T, we get T equals negative, and in this case, it's going to be the ray origin subtracted from the sorry, so in this case, it's going to be the ray origin subtracted from the point on our plane. So a vector from ray origin to P naught, ray origin to P naught dot n over ray direction dot plane normal. So now we have a nice handy equation to solve for t, and then once we have t, it will be trivial to then get our location for the point of intersection. Cool. So let's go back to TouchDesigner and get started. So first, let's just drop down a noise. Now, the resolution of this noise is going to be the number of points that we are instancing. So I'm going to start with 1024 by 1024. I'm going to make the resolution 32-bit float, turn off monochrome, and then just make a few adjustments here. So I'll make the amplitude 2, I'll make the period 2, make the harmonic gain 2.3, and I will leave it here for now, and we'll dial it in a bit more later. So this noise is going to represent our water surface. And as I mentioned before, the direction of our light is going to be coming directly down from the y direction. So this noise is really going to be in the xz plane with a y value of 0. To get our normals, surface normals, which we'll need to use in refraction, we'll use this normal top. And to understand what's going on in the next step, let's take a moment to look at the function that we'll use to calculate the refraction. And that function is actually native to OpenGL, and it's simply called refract. So refract takes in gen type, which means you can use it for any length vector. Takes in the incident vector, which is going to be incoming light, the normal vector, which is going to be the normal of the surface that is refracting the light, and then a float, which is the ratio of indices of refraction for the two mediums, the medium that the light is coming from and the medium the light is passing through. Index of refraction is just a mathematical value that determines, or rather represents, how much light is scattered when it passes through a medium. So we're going to use common values for water and air, which I'll get to in a second. So to get our normal into the format we need it, let's take a quick look. If you open the viewer and hit D on your keyboard, you'll notice in the bottom left-hand corner of tops, you can actually see the values for each pixel, which is super helpful for debugging. As we'll notice, the R and G values here are representing the X and Y normals, and then our B value is the normal in the Z direction. Because our up direction in this project is actually going to be Y and not Z, we're going to use a reorder top to simply flip the blue and green channels. And when we take a look at this, we'll now see that the G value represents our Y, and R and B are representing X and Z. So we now have this normal map oriented on the XZ plane and will be directly usable in our calculations. So from here, all we need to do is create a GLSL top and jump in. Man, I really wish they would figure out a way to actually make trusting folders work. Anyway, let's get going. So, all right, first things first, we need to read in our normal vector. And let's be a bit more specific and say surface normal. And this we just want to be a vec3, so I'll just grab the first 3 values. All right, now we need light direction. So we'll have another vec3, we'll call this light dir. And as mentioned, this is going to be coming directly down in the y direction. Now we'll calculate our refracted light, and we'll do that using the refract function by passing in the light direction, the surface normal, and then for the index of refraction ratio, we'll use 1.0 divided by 1.33, which is the index of refraction of air. Fraction of air, and 1.33 is the index of refraction of water. So there are other surfaces or other materials that have different values here. I will leave it to you to go check out what those are and make some changes here if you like. I find that these values are pretty handy for this simulation and result in nice visual effects. All right, so now we just need to build our intersection plane array and then calculate the intersection. So I will first create the plane normal, which is going to be, as I mentioned, directly opposite the light, so directly up in the y direction. Points up in the y direction. And then a point on the plane, which we will call P naught, is going to be equal to 0 in the x direction. So this is going to be on the y-axis, but we don't want it at the origin exactly. We actually want it a little bit lower than the origin. So I'm going to set it at negative 0.5, negative 0.5 in the y direction. And what this is going to do is set the intersection plane a bit below our refractive surface. So then, if we're thinking about it, this is going to be our surface. This is going to be at y equals 0. And then this is our plane at y equals negative 0.5. Cool. All right. So now we have our plane. Now we need our ray. So our ray origin, our O, is going to borrow a technique from ray casting, and we're actually going to use the pixel for the beginning value for our ray origin. And because we're in the XZ plane, we're going to take the pixel U value as our X. We're going to set the Y value to 0, and then we're going to take the pixel V value as our Z coordinate. Now, our ray direction is just going to be our refracted light vector. And then all we need to do is calculate t using the formula that we have figured out right here. So that is going to look like this. Float t equals negative dot RO minus P naught, and then the plane normal divided by the dot product of the ray direction and the plane normal. Second array with a plane, and then all we need to do is, using the parametric representation of the ray, calculate the point of intersection with the ray origin plus the distance times ray direction. Oh, and one thing I should have done up here is just normalize refracted like this so that we have a unit vector for our direction. Finally, all we need to do is output p-intersect, and we'll see by inspecting this that now we have some points that are represented with RGB values. You'll also notice that the G value, meaning the Y value for all of these points, is negative 0.5, which is exactly the value that we set for our intersection plane. So we have a bunch of points that are all lying on our intersection plane with different XZ values for their location on that plane. All right, so before we go any further, let's call this pose, and we'll do a quick rendering setup so that we can see what we're working with before we move forward here. So to do that, I will create a box. Set the size of the box to 0.1. It's generally best not to do instancing with geometry lower than that size value. You run into some weird floating point arithmetic sometimes, and generally find it best practice to keep the instance geometry at that size or higher. So all that means is we need to scale out our sim, which doesn't really impact anything. So let's get a camera, a light, and a render. Now, because I'm on the XZ plane as well, I'm just going to rotate this geometry 90 degrees. The x-axis, turn on instancing, set my translate op, and then instance my geometry. Let's get a null and display it. Okay, so this does not look so great. And the reason for that is because our boxes are huge relative to our point values, which are all in 0 to 1. So what I'm going to do to work on some of this is first just pop in a math. That math will just multiply by 100. And that's going to get our boxes way, way more spaced out, and already things are looking a little bit better. Tweak the camera location, maybe 180. And now you'll notice that we're obviously in the wrong part of the screen here. That's because our values are from 0 to 1. So we can add another math and just convert those values from 0 to 1 to -1 to 1 in the R direction and -1 to 1 in the B channel, leaving the green channel untouched because that's just our flat y equals -0.5 channel. Cool. So let's tweak a few things to get this working. Make our render a square. We'll zoom out a bit more on the camera to see the entire piece that we're working with. There we go. And then let's try and get it centered. So one thing that you probably noticed when we were inspecting our points here, that we're mostly in the range 0 to 1, but we actually get slightly negative in some areas. So that's why we're seeing a very off-centered rendered grid at the moment. So if we look a little bit deeper by using an analyze top and look at the minimum, and then we'll do a top 2, we can see at the minimum value for red and blue channels is about -0.6, or sorry, -0.06. And if we just check the maximum value, that's going to be roughly about 1 minus that minimum value. So we're really just on the interval 0 to 1, but shifted down by roughly negative 0.06. So all I'm going to do is just pre-add that, which is a little bit of a hack, but in this case, pretty much all you need to get things a lot more centered and looking nicer visually. So one thing I'll also do here is just give us some animation with abs time.seconds. And cool, so now we have our grid moving a little bit, and we can finish dialing in this noise to get some better visual effects. So I'll just turn up the harmonic gain, and now we can already see a caustic pattern appearing, and that's looking pretty nice. Let's take our camera back in so that we're filling up our full screen here. We will add a transform to go to a black background, and we're already kind of cooking. You can see here that if we tweak the noise a little bit in either direction, such as the exponent or the amplitude, our visuals are changing. So there's definitely a lot to be played with here, and you can really optimize this to whatever your specific needs are. Another thing you'll notice is, especially if we look at the top viewer, because we're just instancing points and those points are being moved in space based off the refracted rays, in areas where the surface is flatter, the points are not really moving that much, which gives us these artifacts where you can kind of just see that there's a grid that we're distorting. It's not terrible, but perhaps you want it to look a little bit less sharp, so we can throw a little bit of post on here and improve things. I'm going to use a Luma blur to do this, and I'm going to tell it to blur only the black areas because the white areas represent our highest concentration of refracted rays and our caustic pattern. So I'm going to blur just the black areas. I think maybe a blur of like 5 could be good. Set the white to 0. And then we're going to just blur this a little bit more. Pre-shrink of 2. And this is going to be our Luma lookup for applying the blur. This blur is nice. Let's see if we bypass it. Things get a little bit more hectic. The reason this helps is because it is blurring all of the pixels, especially in the areas where there is less of a concentration of our refracted rays, getting rid of some of these single dots, which still have RGB values of 1, and that would result in the white filter instead of the black filter being applied in the Luma blur. So we do a blur pass to get that Luma lookup map a little bit smoother, and then only apply blurring on the black areas. So like I said, you can dial this in. I like it somewhere around 5, maybe just a little bit more. I like it around 5. And yeah, that's already looking a lot better. Another thing to mention is as you change the period of the noise, you'll probably find that some of these other parameters need tweaked to bring things back to a visually realistic zone. So just be cognizant of that as you're playing around. All of these parameters will want to be changed kind of in synchrony, but there's a lot of flexibility within these different parameters, so you can really have quite a range of different effects going on from, yeah, what is ultimately a pretty simple simulation. So I will leave it there for today, but potentially we'll be doing another set of tutorials on caustics. Later, we can go into things like how to make them interactive, a couple extensions for the effect, and Would also love to see what you guys do. So as you have your ideas, make sure you send them my way.